Welcome back to my Aurora Forecasting Series. This is Michael, and it's time to talk about Aurora event case studies. Woohoo! I know, don't get too excited, but don't worry, it's not as bad as it sounds. I hope. I'm going to look at two scenarios from the past and take a look at the data that led up to a particular northern and southern lights event and talk about the results. The goal here is to prime you for pattern recognition for future events, and that should help you interpret the data that I helped you find in part 3. Both events that I'm going to cover here I actually teased a little bit earlier in this series, so we're going to take a much deeper look at those. This video is meant to be reasonably watchable even if you haven't watched the other 3 in the series, but if you'd like, you can click here in the upper corner to start from the beginning. Let's jump in with a very recent example. Over the summer of 2019, a rather large coronal hole appeared in the sun. Large enough, in fact, that every 27 days or so, as the sun rotated on its axis, it reappeared on the Earth-facing side of the sun and did so several months in a row. Using the imaging tools from SOHO and SDO, we could see this large gap in the corona. Stereo A also showed us that these holes were staying together even when they rotated out of view from Earth. As mentioned, coronal holes can allow a faster solar wind than normal, and this can result in an uptick in aurora activity further south from the Earth's polar regions. Normal solar wind speeds are around 300 kilometers per second. For comparison, the ISS flies overhead at just under 8 kilometers per second. So we're talking enormous speeds here. In spite of the sun being 150 million kilometers away, these weak winds leave the sun and arrive near the Earth in just 5 to 6 days. Winds of this strength result in aurora no stronger than a KP of 2, limiting aurora viewing to traditional places like Alaska, Iceland, northern Norway and Sweden, and Antarctica. 2019's strong coronal hole was so reliable, in fact, that aurora chasers like me were actually planning trips to intercept these weeks in advance. Coronal holes typically produce wind streams of 400 to 700 kilometers per second, or on average about double the speed of normal solar winds. Once a coronal hole rotates toward Earth, there is about a 3-day lead time to wait for the stronger solar wind to arrive at Earth. So if you can plan a vacation or a road trip on relatively short notice, you could have at least a week or more of lead time to work with. Generally speaking, winds of this strength are good enough for around a KP4 and sometimes a KP5. Which means locations a bit further south can see aurora than when the aurora oval is at rest. Southern populated areas of Canada, the border states of the US, parts of Scotland and southern Scandinavia, the northern Baltic states, and St. Petersburg. Bear in mind, however, that in the heart of summer, these European locations have very short nights and it might not get quite dark enough to see aurora. Helsinki, for example, never escapes nautical twilight in June, and of course, that twilight is going to be right where the northern lights would be. Southern Canada and the northern US states, however, still experience enough darkness in midsummer to view northern lights anyway. Now, this handful of coronal hole events, however, were a bit more on the high end, in the 700 kilometers per second speed range. A brief KP of 6 is not out of question at these speeds, and in fact happened for a few hours in June. It brought northern lights deeper into the United States and all of Canada. During solar minimum, there are many coronal holes. Sometimes they appear 3 or 4 times each month. Most of the time, these will only trigger weak KP3 or KP4 events. Given this larger hole producing faster solar wind, the first chance I had came in early June. I went way north to Manitoba, Canada, but alas, was thwarted by a thick haze from wildfires raging way over in Alberta. It was a fun experience nonetheless, and as of then, I can now say I've been further north than the Keweenaw. The second chance came in July when I spent a couple evenings in the UP of Michigan. This time, however, my timing was poor. Had I been up there a couple days sooner, it would have worked out, but this trip wasn't specifically for northern lights. I just happened to plan a vacation for around that time. Then in early September, again fighting bad weather at first, I was able to catch a wonderful display at the Canadian border on the third and final day that they were active. 27 days later, in late September, I made another rather risky trip up to Manitoba again. If you want to see me suffering through cold rain in the middle of nowhere to catch this event, check out this video if you haven't seen it. This final time, however, everything came together. I was able to take off work, make the trip up north, and the weather managed to cooperate just well enough, and the results were absolutely everything I could have hoped for. Even better, I was able to compare a relatively inactive day to an active one. A difference of a KP of 2, or completely average, and a KP of nearly 5, or in other words, a minor geomagnetic storm from a location in southern Manitoba. Notice that on the inactive day, it's clear that there is green and red on the horizon, but not much structure and no movement. These are also quite dim by comparison. I have a lot of experience taking pictures of weak aurora, and I could tell they were there visually on the horizon, but only subtly. I'll take a deep dive into photography and observation in the next installment of the series. During a more active aurora, you could see the same sort of thing happening early in the evening. However, as local midnight approached, and you may remember me stressing this in the first video, the activity surged. It's not that the solar wind changed dramatically, but that being on the opposite side of where the sun is, or local midnight, is where the aurora are the most likely to be viewed and also be at peak activity for a given location. Now, solar wind speed isn't the only parameter we have to be concerned with. The magnetic polarity of the solar wind needs to point south. We want to see polarity, or BZ value, negative. ACE and Discover are in between the Earth and the Sun, so all new data will be about 40 to 45 minutes into the future. Temperature and density during coronal hole events rarely matter much, but higher is generally better. More or hotter solar particles smashing into Earth's magnetosphere can result in more activity. Magnetic polarity of solar wind from coronal holes often varies widely from one hour to the next, and are more appropriate for nowcasting, a slang term often used by normal weather enthusiasts that just means understanding what's happening in any given moment. Surges and short storms during an event can be predicted by simply watching the magnetic polarity of the solar wind. Positive numbers will suppress aurora, or shields up, while negative numbers mean a surge in activity is coming, or shields down. Personally, I notice the most dramatic northern lights when I see the BZ, or polarity number, as large, but with a negative value from that of the BT number, or magnetic power. Think of BZ as our Earth's shield strength, or its defense, and BT as the potential of the solar wind, or offense. To get more exciting aurora further from Earth's poles, we want to see more power, or more offense, and less defense. The magnetic polarity bounces around wildly during a given coronal hole event. Sometimes there will be 30-minute to hours-long stretches where BZ is positive or negative. If it is positive and northern or southern lights are weak, in most cases you can just give it some time and it will flip back around. This generous coronal hole gave us no less than 5 opportunities to see northern lights from the US and Canada in a highly predictable fashion. Events this predictable, this far in advance, don't always happen though. Watch SOHO, stereo, and SDO imagery for these holes, specifically the ones near the sun's equator. Wait 3 days for the solar wind stream to arrive. Use ACE and Discover to confirm when the solar wind has indeed arrived. Check to see how the BT and BZ values are responding to that solar wind. Then use ovation data to track the predicted auroral strength. Here are some lessons learned from the cyclic aurora events of summer 2019. Large coronal holes are generally common during solar minimum. Solar minimum doesn't mean aurora cannot be viewed in middle latitudes like the northern US, southern Canada, northern Europe, and outside the extremes of northern Scandinavia. Coronal holes can sometimes be repeatable events each month as the sun rotates and brings coronal holes back around toward Earth. Lead times can be over a month in some rare cases. Solar wind speeds on the order of 500 to 600 kilometers per second, with BT values over 5 and BZ values under 5, are capable of KP levels as high as 5. 700 kilometers per second, with BT values over 10 and BZ values under -10, can result in KP levels as high as 6, with aurora visible as far south as places like southern Michigan, Denmark, and the extremes of the South Island of New Zealand. At this point, it's just a matter of looking for them with your eyes, or like I mentioned before, your camera. Viewing potential increases around and on either side of local midnight, which by the way can be 1 a.m. in the summer due to daylight savings time. Earlier in the series, I mentioned that coronal holes aren't even the exciting way that auroras can be produced further from the poles. There's another. Coronal mass ejections are a different event that can allow us to see northern lights from much more southern latitudes. At the time that I'm saying this, it's actually pretty close to solar minimum. There are very few sunspots and therefore very few flares, especially flares that might produce CMEs. So step 1 to predicting coronal mass ejections, we're going to need more solar activity, like we will have in the mid-2020s. As solar activity picks up, coronal holes actually appear less often. A busy solar disk means there's just no room for holes in the sun's outer atmosphere. As solar maximum approaches, sunspots will begin to appear more frequently. When they do, it's time to start watching out for much bigger aurora events. Just to get it out of the way, CMEs can be produced by events other than solar flares. But I'm going to leave those conditions out because they're not terribly predictable, nor common, nor all that powerful, and they mostly happen during peak solar activity anyway. This sunspot activity comes in a cycle every 11 years. The next one should start to ramp up in 2021 and peak around 2025. But it's not a sharp peak. The few years on either side of a solar maximum will be pretty active. By late in 2022, sunspots will be common, major solar flares frequent, and minor CME events will already be happening on a pretty regular basis. For this case study, I'm going to break down the 2003 Halloween storm and walk you through every stage of the forecast. First of all, 2003 was not far off the peak of a solar maximum, which occurred in 2001. Sunspots were large and numerous around this time, but size isn't everything. You don't just want a large sunspot. What we really want is a complex one. Magnetic complexity is a bit like twisting up and stretching rubber bands. A little stretching won't necessarily cause any trouble, but too much stretching and it might snap. This is a little bit like what's happening above a sunspot. A sunspot is in fact a cooled area on the sun's disk thanks to this magnetic tangling. If this tension is released suddenly, a flare may occur. We can use SOHO or SDO's magnetic imager to see complexities in a sunspot. The more wild looking this magnetic looping and stretching, the more likely a strong solar flare may result from that sunspot. Some sunspots don't produce any flares, while large complex sunspots might quietly traverse the sun only to explode once the sunspot is out of view. So that's the next stage. Not only do we need a large complex sunspot, it needs to release its energy in a flare while in this general area of the sun's disk, which is the most likely to direct a blast in Earth's direction. Then there's the size of the flare itself. A and B class flares are very minor and not important. In fact, during solar maximum, there is so much X-ray activity on the sun that they may even go completely unnoticed by detectors. Flares are measured like the earthquake Richter scale. Each class up the letter scale represents a 10-fold increase in X-ray power, while a number between 1 and 9 next to that class represents a value somewhere in between each letter level. A C1 solar flare is 10 times stronger than a B1 solar flare, while a C1 solar flare is just a little more powerful than a B9 solar flare. As we get higher into the C-class solar flare range, things start to get more interesting. We start to see the chances for CMEs once we get higher up in the C range of solar flares. The next class up is the M class. The scale changes because now we're talking about major flares. However, major might sound a bit more hype than it ought to be. M-class flares are way more likely to produce a CME than a C-class, but its overall impacts here on Earth are going to be quite minor. X-class solar flares are the next class up, X for extreme. Now at this point, an X1 solar flare is already 100 times more powerful than a C1 solar flare. X-class flares, most of the time, produce CMEs. X is the final letter, so an X10 is 10 times more power than an X1, and an X20 solar flare is 20 times more power than an X1. Not all large flares produce CMEs, but the largest flares almost always do. How do we know if a flare resulted in a CME? The earliest clues come from the GOES X-ray detector. All flares will appear in this data. However, flares that come with a CME will generally last longer. Rather than a quick, sharp spike, you'll see a slow cool down of X-rays leaving the sun. These don't correlate perfectly, however, and we need to look at something else to know for sure. Once a CME happens, we usually have about 2 days before it may arrive, so we have lots of time to pinpoint what happened and whether a CME is on its way or not. We can even figure out the polarity of that CME to see if a major aurora event is coming or a more minor one. SOHO's LASCO coronagraphs allow us to see material leaving the sun. SOHO sits between the Earth and the sun, so we can use the coronagraph to tell us what's coming directly at us. And what we are looking for in particular is not just a chunk, headed only left or right away from the sun, but something called a full halo. A full halo CME happens when it appears that the CME left the sun evenly in all directions. What's happening here is that the CME is squarely headed for Earth in this case. We often know something really exciting is happening when the coronagraph's imager completely loses its mind immediately after a major flare, as it gets baked by X-rays and radioactive material. The Halloween solar storm of 2003 was a great example of all these things coming together several times in an extraordinary fashion. Though don't get me wrong, there have been dozens of events like this, but this particular one, however, perfectly illustrates something right smack in the middle between a typical CME event and the worst case scenario where civilization is knocked back into the 19th century for a while. The Halloween storms started with a new sunspot, 484, forming on the western limb of the sun's disk on October 19th. It almost immediately began producing X-class solar flares. This flare also produced a CME, but it would shoot off well behind Earth's orbit and not cause any impact. But that sunspot is moving east as the sun rotates, so any events in the next few days that produce CMEs may be Earth-directed. By October 21st, sunspot 484 grew to an enormous size, but had also gone quiet. This can be an ominous sign. Very large, complex, quiet sunspots are like taking a large wad of rubber bands and stretching them all to their breaking point. Something's probably going to give any minute. On October 22nd, there was an M9 solar flare. By now, sunspot 484 was very near the center of the solar disk. This flare would result in a CME, but still not quite squarely Earth-directed. The thinking was that it might have just delivered a glancing blow to Earth's magnetic field with a small chance of northern lights. No matter, early in the morning on October 23rd, a massive X-class solar flare occurred, this time yielding a full halo CME that was likely to be intense. On October 24th, a pair of CMEs arrived at Earth. The event was strong enough to cause a KP7 Aurora event. Keep in mind, this isn't even the main show, and places as far south as Germany were spotting northern lights. Unfortunately, this preview event didn't last long enough to be seen in North America. On October 25th, another gigantic sunspot, number 486, appeared over the sun's western limb, and this one too had begun producing large flares and CMEs right out of the gate. October 26, sunspot 486 unleashes another X-class solar flare and another CME. This is where things really start to get nuts. A CME is already on its way to Earth and expected to arrive in a couple of days. The velocity of this wave was probably on the order of 800 to 1,000 kilometers per second. In other words, the expected time for this wave of particles of strong solar wind would take just 48 hours or less to arrive at Earth, when Aurora could be expected. More M-class major flares followed on October 27th, as Aurora chasers patiently awaited the arrival of the next CME. Then the big flare came. On October 28th, an X17 class solar flare erupted from the massive complex sunspot 486. A thick, extremely bright, full halo CME left the sun faster than 2,000 kilometers per second. Around the same time, the CME that left the sun October 26th had arrived. Unfortunately for Aurora enthusiasts, the interplanetary magnetic field tilted north during most of the event. In this case, unlike coronal holes, sometimes the entire duration of a CME event, which lasts anywhere from 6 hours to 2 full days, the IMF direction of the CME matters very much. It can tilt way north, suppressing Aurora, or tilt way south, resulting in a major event. But this X17 class solar flare, let's put that into perspective. The previous CME was propelled by an X1 with 1,000 kilometers per second speed. An X10 flare would be 10 times as powerful as this. An X17, however, is 17 times as strong. This flare and CME were about to be extraordinary. Because a huge shockwave had already just left the sun, the next shockwave, propelled at least 2,000 kilometers per second, wasn't going to encounter much resistance. So much of that speed is going to be maintained all the way to Earth. This happens often during big events. One shock wave clears the field, if you will, and another bigger shock wave easily travels through its wake. Indeed, less than 24 hours later, a measured solar wind gust exceeding 2,000 kilometers per second arrived at Earth's magnetic field, providing a giant wallop. Many solar wind sensors were overwhelmed. ACE measurements were entirely unusable during the event. Later, the data was reanalyzed, and it's possible that for a moment, the shockwave arrived at Earth with a relative speed of 2,240 kilometers per second, and it had arrived just 18 hours after the CME left the sun. This time, the IMF tilted deeply south, and the results were one of the strongest Aurora events ever tracked during the space age. Many hours of KPs of 9 were happening. The BT, or power, over 50, and the IMF in the minus 40s. Aurora were spotted in places you just don't expect them ever. Texas, Florida, Italy, the North Island of New Zealand, Sydney. Images of auroras flooded the internet from all over the world. Unfortunately for me, in the upper Midwest where I was living, I was dealing with clouds for most of the event. But the days that followed after this event, I did much better. Late on October 29th, an X10 class solar flare occurred and another CME. This CME would arrive just 24 hours later, early on October 30th, and was almost as powerful. The result was that before the first event had ended, it was replenished, and this kept the entire Aurora event going until late in the evening of October 31st, Halloween, for which this storm gets its nickname, the Great Halloween Storms of 2003. Here are some things we can learn from this event. X-class flares usually produce CMEs. Very large sunspots are capable of X10 and higher class solar flares. Flares coming from sunspots near the center of the solar disk, as viewed from Earth, are the most likely to bring impacts to Earth. Normal, weaker CMEs can take over 2 days to arrive. the most powerful and fastest CMEs might only take 18 hours. Sometimes the IMF points north and the entire event can be squashed. So if you plan on traveling closer to where auroras might be more visible, keep an eye out for modern modeling data that can tell us the likely polarity of a CME before it arrives. KP9 and higher events do happen, and places like Southern Europe and the Southern US can see northern lights when this happens. In order to get a KP9 event, we need a very large, very powerful CME capable of producing solar winds in excess of about 1,400 kilometers per second, with BT levels over 30 and BZ levels of -30 or less. These events are most likely during the heart of solar maximum. You've made it. You just survived 2 very different case studies, got to look at some real data, and actually see the end results. Now I can finally get to the really fun stuff next. How about aurora observation and phenomena, taking photos and time lapses? Then we can talk about doomsday scenarios, aurora tourism planning, and the like. Each of these next videos would be great standalone watches, but also a continuation of the series to help you learn more. But now, having watched this series, you'll have tons of context to help us through the technical details of what I might drag us through next. I really hope you enjoyed this video, are enjoying this series, and can't wait to see more. Thanks again for watching. Thanks for all the likes, comments, and subscribes too. Everything you do helps this channel grow. And my hope is that future generations of space weather enthusiasts find this series. And if that's you, welcome aboard. And to everyone, I hope to see you out there.